Thank you for being here. Let's talk this morning. David Dalrymple, also known as Davidad. I've been collaborating with Davidad for a number of years. He has an extremely sharp mind and has been focusing on the question of risks, and especially lots of control of AI and how we can get guarantees, which is the purpose of this workshop. And he's a program director at ARIA in the UK, a program that is funding this kind of research.
All right, thank you, Yashua. Yeah, so I'm the director of a program at a UK public sector funding body called the Advanced Research and Invention Agency. And this is basically going to be a smorgasbord of research topics in that program, but starting with a sort of overview. Let's see. So first of all, like, what is the problem we're even trying to solve? It is not, let's take LLM chatbots and make sure that they're safe or sort of formally verify that they're safe. That does not seem tractable when they have dangerous capabilities, and when we haven't got jailbreak robustness, then certainly it wouldn't be verifiable. It isn't true that it is safe. So what can we do instead if we can't make the kind of AGI chatbot actually be safe? The idea is, we think of the AGI chatbot as a resource analogous to uranium. And uranium is dangerous by its nature, but it can still be used to provide lots of economic value to millions of people around the world. The way that you do that is you put it in a very well-engineered container. And for illustrative purposes, cut a hole in it, show that it's in there. Yeah, don't actually cut the hole in it. And the idea is that you harness this to produce tool AIs that are narrow, domain-specific agents for decision support or for automating particular things. And on the way out, before coming out of the container, you formally verify that these narrow systems are actually compliant with their specification, which is some quantitative thing. So that's the kind of concept, is how can we take systems that are dangerous and cannot be made safe, in case we can't make them safe through other means, can we demonstrate an alternative deployment solution that can still produce lots of revenue without actually giving people direct access to the very dangerous material? So now I'm going to talk about what I mean by quantitative guarantees and verification. So there's essentially three pillars, three parts to getting quantitative safety guarantee in this context. The first part is you need to have a mathematical model of the task, of the context of use in which the task is to be performed. And what that means is essentially a model that can predict, given some intervention that is made by the system, whatever its affordances be in that context of use, an imprecise probabilistic prediction of the future effects of that intervention and how that will roll out in the context, and including all effects that could be relevant to harm that would be causally attributable to that action. And this is a auditable kind of symbolic or mostly symbolic component. May contain some neural approximations, but they should be of low-dimensional things that can be validated in other ways, like by doing lots of simulations and by doing Bayes factor calculations and making sure that the model actually fits data. But mostly, this should be an understandable thing where it has a lot of variables that have names that people understand, and they should be able to do something like code review, very analogous to kind of the way that large companies do code review. You have 3 humans who need to sign off on each piece of code before it gets committed into the world model repository. And the goal is not that this model be accurate. An important aspect of this modeling framework is it should be imprecise probabilistic, which means it contains the true probability distribution. Go ahead, Daniel. Yeah.
AI in this first column means the tool AIs.
That's right. That's right. Yes. So the tool AI that comes out, not the AI in the box. So once you have the world model of the narrow domain for a particular tool AI, and this is like the workflow that you would do maybe thousands of times for many different tasks across the economy. So for this given task, you've modeled the context of use, then you need to define success and failure. And my kind of working concrete hypothesis for what that means is you have a conjunction of linear inequalities about reachability probabilities of conditions relative to that state space. So there are some things that you would like to reach. There are some things that you would like to not reach. You want to put an upper bound on the probability of reaching hazards or harmful or unstable conditions. And these are things that are fundamentally of a different kind in a couple of ways from the world model. One is that specifications could include hyperproperties. So they could include inequalities that are not representable as the expected value of something that is a variable in your state space. And the other thing that's different about it is that specifications cannot be validated against data because they're fundamentally normative. So someone needs to be responsible for determining whether the kind of risk criteria are appropriate for all of the conditions that are hazardous, and that should really be done by a collective deliberation rather than just having one person do it. Say again?
I didn't follow the hyper bit.
Hyper property is a property which is not expressible in terms of the expected value of a function of the trajectory. So it sort of is fundamentally a nonlinear property of the distribution over trajectories. So saying like the probability of reaching a harmful state conditional on the AI action minus the probability of reaching a harmful state conditioning on no action is less than some threshold 0.01. That is a hyperproperty. It's not expressible as an expected value. Go ahead, Rick.
I think also counterfactual queries
Yeah.
like a very, very high bar because naively it seems like you have to model the entire rest of the world in your spec to say what would have happened if you hadn't deployed the system.
Well, that's where the imprecision comes in. So if you don't know, you can declare variables, especially exogenous variables, as being essentially non-deterministic. You may be able to put bounds on them and say it's within this interval for reasons like conservation of energy, or just like for kind of spec sheet reasons, like, oh, the temperature will not be greater than 150 degrees. And
these things to be useful, like collectively those bounds will have to remain tight enough that they don't, add up when you just say, well, something's gonna happen, we don't know what it is, right?
Yes, that's right. So this sort of only makes sense for contexts which have kind of controlled conditions. And I'll come to what like a set of contexts shortly, sort of a bunch of illustrative examples of where this might be useful, but it's not for everything. Yeah, Michael.
So I think when you were saying, like, compared to it taking no actions, that means that you're not trying to compare, you're not trying to take into account the response of people to the existence of the AI system.
Yes. The response of people is kind of part of human behavior in general, which I think we should try to make as few assumptions about as possible. And we should sort of be doing predictive, tracking of things like demand for energy on the power grid and sort of forecasting that based on data, but being like very uncertain about how it will change, particularly over longer timescales.
It seems like for particular people, the imprecise probabilities that you have to assign to them would quickly infect the rest of the world if they have a lot of power.
Yes, I think that's reasonable, particularly over longer timescales. You need to not just sort of roll out for a year and say, no matter what happens, whatever people decide over the next year, this will be fine. These guarantees will probably need to be iterated more like daily. And so as conditions change and runtime monitors get tripped and say like, well, people are behaving in a systematically different way now, you flip to a backup controller and kind of replan based on new data. Yes.
What does the purports to constrain mean here?
So by constrain, I mean put bounds, upper bounds and lower bounds on expected values of functions, as opposed to predict, which kind of implies a point estimate. That's the reason I use that verb. It's still not great because that sounds like it's actively constraining. But what I mean is to model bounds.
Okay.
Okay, and then the final pillar is verification, and this means not just a kind of static verification, although static verification is kind of necessary. Runtime verification is also necessary, but what's important here at this level of abstraction is that there is multilaterally auditable verification, so that many stakeholders can check without getting kind of sensitive information like the actual weights or indeed advance notice of the outputs necessarily. They could be getting zero knowledge proofs that the runtime verifier is checking out in accordance with conditions, barrier functions, things like that that are verified statically. All this could be chained together so that stakeholders can get this kind of verification in the sense of assurance that the system is still operating according to spec in real time. And the idea here, the false positive probability approaching 0% is this is sort of a condition on the correctness of verification. So this is a minimum bar is that the correctness should be asymptotically correct. So that the more compute you put into it, the more likely it is to be correct. Mostly in the Safeguarded AI program, we're actually focusing on verification of probabilistic properties, but where the verification is exact. And so if it verifies, then we actually have certainty about a bound on probability. But it could also be that that ends up being computationally intractable. And we might need to fall back to approaches that have only asymptotic correctness, even about whether the bound is true. Yeah, Jeffrey.
Which compute is that? So it's not the
Verification compute.
It's not the boxed AI compute.
Not the boxed AI compute. The amount of compute that's dedicated to checking the claim that the boxed AI makes and provides evidence for. Yeah.
Sketch like how different amounts of compute verifications look like that fire.
So it's perhaps the best example is Jeffrey's scheme about debate, where the prover and the verifier engage in a dialogue, and the verifier makes choices about which parts of the argument to check in detail. So the more compute you give the verifier, the more intelligently it can make selections about which part of the proof tree to challenge, and also perhaps the more branches it could explore.
It's like a slightly non-standard use of verification.
No, this limit is the definition of verification in a sense. You have a function, you have proof that it is almost true.
Yes. All right. And then I wanted to just connect this to a kind of position paper from last year, which Joshua and I and many others were authors on, which is basically, here is the kind of framework that we all agree on for what it means for AI to be guaranteed safe. And it involves the same three critical concepts. You have a world model, you have a safety specification, and you have a verifier. And the verifier is a kind of gatekeeper that must sort of declare that the AI is safe for a given task before it enters a deployment environment and starts interacting with the rest of the world. And that you have also runtime monitoring. So the verifier continues to check that the assumptions that it made about the world still seem to be compatible with the observations. Yeah, this is a bit of a more abstract, in the paper, our definitions of world model and safety specification are at a higher level of abstraction, but guaranteed safe AI has as a subclass safeguarded AI. So just to clarify that connection. So now I'm going to go into
There's the static verification and the runtime verification.
Yes, so I think static and runtime verification will both be necessary, and I'll talk about that in detail here. I have both in this diagram. So this is my most recent block diagram about the safeguarded AI workflow. And this probably will take up several minutes just to go through all the pieces of this, but I think it's useful to have all of them in one picture. So first, one teams with human level AI that is sort of generally considered safe to interact with, at least for privileged users who are experts in a domain, to produce the world model, which is like the assumptions, mathematical assumptions about the operating domain. And so this is the way it's written here is in the limit of kind of very cheap, very abundant capability, you might just have the human level AIs produce proposals, which are then reviewed and audited by humans. But in the near term, we're going to have also a closing of the loop here where humans provide feedback and there's a iteration on these assumptions and incremental construction and refinement. And then these get fed into the box along with specifications, which, as I discussed, are a different type of formal artifact that is more normative in character. And it sort of depends upon having the world model so that there is a language of state space that can be referred to in the specifications. And the specifications can be produced by the same kind of process, but the type of humans who need to be involved in signing off on the specifications might differ, and it's of a different formal type. Then once you have the specifications and the assumptions, those go into this containment box, which is the shaded kind of tan colored box, which is ideally, I'm not going to probably do this within the program, but when this is actually happening with very risky superintelligent level systems, this should be a formally verified hardware and software platform that sort of gives hard guarantees about confidentiality and integrity, which correspond to information flow into and out of the box that is not according to the workflow. So we want to really contain this thing. It's then got a goal, which is to produce a solution to the problem specification and to also produce a proof certificate. And the blue arrows here are like logical implication. And the proof certificate is a logical implication that says if the assumptions are true and the solution is deployed, then the specifications are true. And there's also a bound on the amount of kind of degrees of freedom in information theoretic terms that the superintelligence may have been able to choose adversarially to make some side effects happen in the world. This is perhaps the hardest part. But if your problem has enough constraints and a kind of optimality condition that some performance objectives in some linear combination need to be minimal, then perhaps you could have a branch and bound certificate that basically says the optimal solution is within a small radius of this proposal. And that could give you this kind of bound. So if there is a unique solution to an optimization problem, then the only causal power that the solver has inside the box is to either give you that unique solution or to refuse and fail. So it only gets one bit of causal power per invocation, if you really can get to optimality. Otherwise, we'll have to come up with some creative solutions for how to bound like the KL divergence from a uniform sampling of things that are at least as good as our bounds or something like that. This is also something that could be done at runtime. So it could be that the solution involves inside the advanced controller that proposes actions, a branch and bound process that produces a certificate that's checked at runtime that this is a kind of nothing up my sleeve optimal solution to the optimization problem in that stage. So then,
Can I just,
yes.
This is, I think, a really cool problem. And I think we were trying to write about this at AT as well. And it's like a very crisply defined information theoretic thing to ask about skill oversight. So like, I would encourage people to think about this. Like, I think it's
it's neglected and very important.
Also, I think it might be shallowly tractable from theory.
It may be.
You talking about the entropy bound?
The entropy bound, yeah.
And we have kind of simpler settings without the rest of this complicated diagram for studying this. So we'll try to.
Great. Yes, Michael.
So what if there's, this entropy is not 0 or 1 bits, but it's like 50 of them.
Yeah.
And it's like the system is, I can imagine we could speak to it. It's like, well, sorry, I'm just not smart enough. I'm like, yeah, sure, it seems like there should be something over here. I just can't figure out what it is.
Right.
or like, yeah, sorry, I'm just not smart enough.
Right.
like, Then, because it seems like for lots of problems, it would genuinely.
It would be hard.
To,
Yeah, yeah.
to bring that down lower.
I think that's right. I think this is one of the trade-offs that might need to be made.
Can I just say, I think you need to solve this, assuming the agent can't get this to the global optimum. So it's like,
Right.
It's within the range of answers that it can produce. That's where you need the bound. And so that makes the problem harder, but I think it might still be tractable. Yes.
Feel free to defer this till slightly later, but I was wondering if you could paint a slightly more concrete picture. Say like the system is proposing economic intervention. You're trying to guarantee that N people aren't worse off, like you were saying. Like, what does that look like to verify this?
Yeah, I think there will be more concrete stuff later, so I will defer that riff. Yeah.
In this vision of things, the humans working with maybe safe human level AI have to produce both the assumptions and the specifications without using the risky AGI or ASI. That already feels like a big lift if you look at like kind of the level of assumptions or specifications we've been able to make as humans so far.
Yes.
Why should we be optimistic that we'll be able to do this for kind of difficult high-level domains where right now like our best solutions are actually quite fuzzy?
So my take on this is that it is hard because there are not many people who know the languages in which these things are written. And that is because learning the language is not very valuable. And that is because once you know the language, it takes a lot of time to do anything useful with it. And people don't care very much about the result. So if people cared about the result, and more importantly, if human level AI time becomes much cheaper than actual human time, and if the AI only has to learn the specification languages once, and then you can copy that many times and avoid the learning curve cost, then I think that changes the equation.
Is another way of saying this that you think that there's like a lot of low-hanging unpicked fruit in the world in kind of formal methods right now, even
Yes.
without advanced AIs, that just isn't being picked up off the ground?
Yes, but I would say it's not being picked up because it would require training, lots more PhD students in formal methods, and it doesn't necessarily make economic sense right now to pick up those low-hanging fruit.
Where do you get the safe level AI?
That's what the rest of this conference is about, right? Prosaic. Yeah. I mean, we do currently right now have AI that, Gemini 2.5 Pro is almost good enough to be really useful in this context, and it doesn't seem catastrophically dangerous. So.
Yeah. Can I ask a sharper question about the quality bound? So
Yes.
I think if I imagine, say I'm doing fluid simulation, and I say there's some like fuzz I can imagine, like perturbation I can imagine at every point in the simulation that's small.
Right.
If that perturbation is random, I'm just adding energy and it'll be similar. If the perturbation is adversarial, I can cause the fluid to like fly out.
Right.
So like what's the intuition for why you don't expect imprecise probability things to stack and produce vacuous bounds after enough?
So I think in the context of statistical mechanics of that kind, then it would be reasonable to have your imprecise probability bound be something like the KL divergence from the Gibbs distribution is bounded by some constant. So it's not anything can happen. It needs to be something that's pretty close to what you'd expect statistically.
But that's exactly when you can say that there's almost no imprecise probability.
I think that's right.
But when you can't say that, why doesn't it explode over time?
So if you have both non-determinism and this kind of like chaotic interaction like you have in turbulent fluid flow, then it would explode over time. Yeah. So that is a limitation on the kind of domains you could work with here. But I think actual fluid flow is not an example where you need to assume kind of adversarial behavior on the behalf of molecules.
So you need a stable domain as well. Physics has to be stable.
Yes, that's right. Yeah. Yes.
This is just a comment because I think we're speaking with adequate sort of sobriety about formal verification and needing to train more students and acknowledging how difficult it is. Having worked in causal discovery quite a bit, I feel we should be adequately sober about that also. When we
Yes.
put that on the slide here.
Yes.
There's a sense in which it's seeming like, we can do this already, and that's clearly not true. So
Yes.
we need to train more students and certainly take the work in this long-standing area very seriously and spend quite a bit.
Yes. So world modeling, causal discovery, specification production, and verification are all three different kind of skills that we need to train people for. We need to train humans to review specifications. Oops. And review specifications and causal models. Yes.
Along those lines of the challenge of building the causal model, and in general, there's going to be many possible causal models that fit the current science.
Yes.
And it's not always going to work that we can just partition it into small pieces that are independently to be chosen. But then this human loop process is not going to work.
Yes.
We
So
need to represent a joint that maybe is structured in weird ways.
a joint that is structured, yeah. So I have, at this rate, I'm not going to get to it, but I do have a slide with a bunch of different ways of composing causal models. And one of the really important tasks that the AI will hopefully be good at here is decomposing an environment into a bunch of chunks, which can be composed by product, by coproduct, by growth and deconstruction, and so on. And then those individual chunks can be filled in with multiple possibilities depending on explicitly, and humans could disagree about which way to fill in each of these boxes, but if there's only a handful for each box, then perhaps we don't have a combinatorial explosion in overall causal models. Yeah. But indeed, this will also be a kind of restriction on the domain. One of the explicit things that I put in my call for proposals for technical area 3 is I said, domains must be known science. So we're not going to do a controller for cold fusion. We need to actually know the causal model in order to apply this. We can have some ambiguity, but it is limited. Yeah. Yes.
Let's transfer entropy down.
Yes.
How important is it for your sort of heuristic model of this that the solution to the problem is unique? I mean, it seemed like implicit in what you said and maybe in what Jeffrey said. And of course, there are some domains where that's true, but I feel like many of the domains you're solving here, it's wildly not true.
Yes. So there is a trick for, at least in the semantic level, solving this, which is that you can impose a arbitrary ordering, like alphabetical ordering of equally good answers to a problem, and then say your unique solution is the least optimal solution in this ordering. And then when you're doing the branch and bound, like that becomes part of what you're bounding. It's where you land in alphabetical order.
In the paper we're gonna hold with this, it's like that's in the, I think it does not work.
It is.
Because I think that does not work.
It is not
I think we need
practically
something
work.
fancier than that.
I agree. We need something fancier than that, but that is an illustrative example. Yes. Okay. Yes.
You mentioned we need to know the underlying causal model for the domain we would release a tool in. Does this kind of rule out certain areas of automation completely? Like you can't have an AI president or
Yes.
an AI Federal Reserve chair.
Yes. I think that's correct. Yeah. So this is basically a solution template for engineering problems, as opposed to science problems or society problems. And there's still a lot, many of the things that people want superintelligence for are to solve engineering problems, but yeah, not all of them. Yeah. Yeah. Okay. Last call, or to move on from this picture. Yes.
Can you say a little bit more about like the picture of training for the risky AI you haven't read? It seems like plausibly the training involves much more interaction with the world and like doesn't work in a box setting, in which case
The training will be with synthetic data, with simulations.
So there's no interaction.
Yes. Well, I would say the simulations should be determined by causal discovery, which is determined by data. And we could have some very simple AI systems that propose experiments to refine the unknown variables in a causal model. But the very powerful system in the box should not be, even in training, directly doing experiments in the real world. That's my view. Yeah. Okay. So now I'm going to talk about the program, which is structured in a somewhat different way from the workflow that, if we complete the program, will be a thing you can do, which is what the previous slide was about. So the program, again, for background, RE is a public sector funding body. We have 59 million pounds allocated. We are nowhere near like spending all of that. I think we're about halfway through even funding, like contracting who will be doing the work. And the program has a lot of technical areas and sub areas. Technical area 1 is going to be all open source, and it's all kind of scaffolding. It's the yellow part and the green part that surround the machine learning. This is sort of analogous to the containment vessel that you put the uranium into. And that includes the language definition. So what we started first and what is starting to make progress is actually having a sufficiently expressive language of cyber-physical system models that has all of these compositional features and that is kind of declarative enough, but also extremely expressive, covers continuous time and so on. So the language for modeling and then consequently for specification and proof, this is a theory problem, not a deep theory problem in terms of like really proving new theorems, but a theory problem in terms of like discovering good syntax and semantics that have good theoretical properties. So that's in progress. Then we're selecting right now people to implement that and implement the kind of version controlled database of these causal models and the process for reviewing them. And then there'll be a human computer interaction layer on top of that for how people can visualize and interact with and manipulate those models and for eliciting specifications. And then a socio-technical layer for aggregating specifications when stakeholders disagree about risk-reward trade-offs. Riff, yeah.
So this lower level, this TA11 seems extremely difficult. I mean, we've had decades of like attempts to define languages for modeling, you know, Petri nets, probabilistic programming languages, this, that, the other.
Yes.
And like, there's always trade-offs between these things. There's no perfect language, but like, you kind of made it sound like you're just kind of in one swoop, like unify all this and come up with like the one true modeling language. So
we're going to unify all of it. We're going to put everything at the kitchen sink in. And the thing that we're going to trade off is tractability of proving anything. And we're going to say, we'll let the superintelligence in the box handle that. We want to make sure the description length is small of both the systems and proofs, but the problem of actually running a query on this, we're going to let the cost of that go out the window. That's the trade-off.
One follow-up though, I mean, like we don't really expect the superintelligence in the box to be able to solve like NP complete or like harder problems in short amounts of time. And so if you define a language where inference in the language or proof in the language is at least as hard as that, even a superintelligence won't be able to do it.
Won't be able to do it in general. I mean, I think there's a big disconnect between worst case complexity and typical cases. And so I'm just, it's part of the thesis here that in typical cases, it actually will work, even though the language is expressive enough that you can't rule out lots of ridiculously impossible problems.
Yeah, I mean, I think the one counter would be like if you watch people who are doing probabilistic programming work, like they often define real world like problems that actually correspond to real world situations, and already turns out to be ridiculously hard, right?
Yes, yes. So it's one of the tasks for the machine learning group is going to be like something that we can do right now is with even existing probabilistic programming languages. Can we massively accelerate inference? And I think probably yes. I think no one's doing it. Or, well, no one except Yashua's group so far. Yeah, I'll skip this. I already talked about the scaffolding. Then there's the machine learning part, which is, yeah, building the domain models, the world models, the specifications in a way that humans can read and react to productively, sort of AI-human teaming workflows. And also part of this is learning to do inference and learning to actually find policies or systems that incorporate neural policies that can be certified and producing the proofs for that. So there's like 4 different kind of machine learning objectives that need to be trained for in here. And then we've just announced a few weeks ago the real world use cases. This is the initial set of real world use cases. So it's really quite broad. There's like, autopilot is like a classic thing for formal verification. But we could also think about construction project management and scheduling, industrial processes like chemical sector, water system operations, control systems for robots and human environments, risk management in insurance and finance, energy system balancing, telecom, supply chain optimization, biopharmaceutical manufacturing, clinical trials, and the list goes on. So these are all areas where I think you could make models. Even this one, education. So like a lot of people talk about AI for education, and most of that, like if you have a chatbot that's a tutor, there's no way you could verify that. But there are some things you can do. You could make a Bayesian assessment where you have some psychological model, a causal model of pedagogy, like what is the student's state of knowledge, and after giving them a module, like what is the probability that they transition to having some additional bits of knowledge. And then you could do planning, probabilistic planning against that and verify that your planning is correct. This isn't a particularly scientific, it's not, you wouldn't generally think of it as engineering. You wouldn't verify that your model is correct. You would know that it's a rough approximation, but it would be a better approximation. It would be more effective probably than just having the chatbot sort of propose what should we talk about next. So a bunch of possibilities. We've narrowed it down mostly to critical infrastructure. And the reason is to reduce competitive pressure to automate control of critical systems using black box AI. And also if we can improve robustness by making these systems able to adapt to changes in the environment very rapidly by updating a causal model, proposing an edit to a human, the human signs off on it, you find a new policy that adapts to the causal model. This could go much faster than other forms of adaptation. And that's for both perturbations from rogue AI and just generally the world changing faster. Yeah. Okay.
When you talk about accelerating inference,
yeah.
Question about, when I look at probabilistic programming, it's like a very complicated distribution from which it's very difficult to sample.
Right.
It doesn't seem to me the problem is that it's slow. It's just that you actually have no real idea how complex that distribution is a priori, and therefore you don't actually know what the computational requirements are to sample. You do Markov chain Monte Carlo, you look at the health indicators, you're like, looks okay. And then you sample.
So this is
like difficult.
It's not sampling. Sampling isn't what we would accelerate. So what we want to infer is given a function over the state space, what is the interval in which its expected value will fall over a finite time horizon. And of course, you can answer that by saying it between minus infinity and infinity, and that'll be correct. And the inference process that I have in mind is something like, as you do more computation, you narrow the interval of the expected value. And that's something that can be accelerated by searching, basically by doing partitions of the state space in different ways, and then doing abstract interpretation on those partitions and getting some more and more refined estimates of expected value bounds, which can relate to each other. You also determining like at which time points do you want to intermediately infer expected value bounds in order to most usefully infer the final query. So lots of things to do there, I think. Okay, these are the 8 use cases that we've actually ended up with. Power grid management, battery management for EVs, which is kind of also a power grid balancing problem, but this is a demand balancing problem, whereas this is not balancing, managing supply to match demand. Managing demand to match supply. Telecom, radio access network energy management is a very kind of narrowly defined demand management problem where basically they're just not bothering right now, at least in the UK, telecoms are just not bothering to switch off channels of towers except overnight. They're like, yeah, for each city, we figure out like roughly when everyone's asleep and not using their phone, and we'll switch off half the channels then. But they just configure this manually. And there's a lot of money on the table to be just doing this more intelligently. But in order to do that, they need to have more confidence that it's not going to end up denying service when people do want it. So this is one that is kind of essentially dependent upon predicting demand, which is something that's kind of human behavior, but it's aggregate human behavior over a large population within a city. So I think we can do something useful there. Self-driving car safety monitors. So this is, again, not for the perception part. That's too hard to verify, although it could be done in principle with inverse graphics. We don't have the compute for that. That's a future thing. This is just at the level of abstraction in which the car has done all its perception. It knows where, it thinks it knows where it is. It has some estimate of where it is and where other obstacles are. And it's trying to plan a maneuver, and you want to make sure that that maneuver has a very low probability of harm, even if the other cars take some unpredictable actions. So that's something we can help with. Predictive maintenance, specifically for road and rail bridges. I didn't specify this. They came in saying predictive maintenance, and then they determined that road and rail bridges are the most suitable because they're very valuable. They're neglected. There are very large portfolios. That is, there are not enough civil engineers to kind of manually make the decisions in an intelligent way. The clinical trials, so there's 3 that are kind of biopharmaceutical related and perhaps will help with resilience to biorisk, at least a little bit. So being able to run clinical trials much faster and more efficiently and still get the same amount of evidence, being able to better manage disruptions to supply chains and spin up new supply chains very rapidly, and being able to do much cheaper and more widespread manufacturing of advanced biopharmaceuticals and sort of automate the quality control. So those are some of the use cases. In technical area 2, which is the machine learning area, where we're going to be developing systems that are good at things like mathematical modeling and doing this kind of expected bound inference and finding proofs about policy, reach avoid specifications, and then actually training the policies such that they have short proofs. So these 4 things are all like very dual use. And so we want to put this in an organization, a host organization that has very strong governance and security, information security and cybersecurity. So right now, there's a call for proposals out until April 30th for people who might want to help create this type of institution and host some researchers who will do this work. Yes.
Just to not make sure I understand the big picture.
Yeah.
Right now we don't have the red box with the unsafe super AI.
That's right.
In it. So are these all areas where you're kind of using them as like test areas to kind of test the workflow without having that box, or do you need that box to get the results in these areas?
These areas. So we're asking each of these companies to produce a curriculum over the next 2 years of initially extremely simplified and over time more realistic versions of their problem. And the plan, or sort of my median forecast, is that by the end of those 2 years, we will have the red box and we will get those results, but we could not solve their real problems this year. That's true. But we can solve toy versions of the problems this year. So let's see, I only have a few minutes left, so I'll skip through some of these. This is on the probabilistic reasoning. So this is just an idea which is inspired heavily by the GFlowNets concepts from Yashu's group, which is to take small language models which are large enough to somehow have some seed of being able to predict stuff in a pretty general way, and then train them using a GFlowNets objective to answer queries about probabilistic programs and read out the answers from the logits of a forced choice or something like that. And the loss function can do things like penalizing the inconsistency of probabilities using various kinds of inequalities that are necessarily true of any consistent probability measure. Yes, sure. Yes, there are also some equalities. in imprecise probabilistic models, there are fewer equalities. I think that's the reason.
Let's think that way.
This is a really interesting piece of work that has actually come out of the program, even though people only started working on it about 6 months ago. This is a new proof method for reach, avoid, stay properties of controllers that could be neural networks that could be operating in continuous time with a continuous time dynamical system. And the way this works is you define a function v, which is similar to a value function, like the solution to a Bellman equation, but it is more like a over approximation to the Bellman equation. So the conditions are it needs to be decreasing over time. So in the continuous time version of this, it's actually a property of like a stochastic derivative, which involves Feller processes. And essentially, this is saying the derivative of the value function over time has got to be less than or equal to some strictly negative function of time. So it's got to be decreasing over time. And in the desired state, it is less than, there are 4 kind of levels. So in the desired states, or there exist these 2 levels, beta and alpha, which whose sublevel sets are within the desired state, the goal state. There are these 2 other thresholds whose sublevel sets do not intersect with the hazard state. And what these conditions essentially say is that if you start in the initial zone, which is inside of the 3rd level set, then you will eventually go into the innermost level set and stay within the 2nd level set. So and during none of that time will you ever get to the hazard state. So that's why it's called reach, avoid, stay. You will reach the goal while avoiding the hazard, and eventually you stay in the goal. This is an example of a trajectory that passes through the goal state without actually staying there, but it's still eventually on a trajectory that forces it into this innermost sublevel set in which it will actually stay in the goal. So this function, the function that defines these level sets, is something that needs to be discovered, and it can be trained. Like all of these conditions can be turned into terms in a loss function, and the function itself, just like in approximate dynamic programming, where in reinforcement learning, where you learn a value function as a neural network, you can learn this proof certificate as a neural network, and then verify that the conditions are true using verification techniques like a ReLUplex or SNT or semi-definite programming sum of squares things. So this is it only really makes sense in low dimensions because doing this verification isn't really tractable in high dimensions. But this is like a low dimensional primitive that could be composed into proofs for more complex systems and can be really flexible in terms of the neural network can kind of adapt to the continuous time dynamics of the system and still give you this really crisp, proven quantitative property about the probability of reaching the goal and avoiding the hazard. So I think I'm about out of time, so I'll stop talking here and take remaining questions. Yes.
So I think you're trying to avoid having to do alignment of the red box.
I am, let me rephrase that. I am trying to construct a plan for handling the case in which we cannot align the red box, and yet people still have tremendous motivation to extract money from it.
Sure, that is the same thing, I think.
I'm just rephrasing. I think
there's another kind of intermediate goal where you could imagine avoiding having to solve specification.
Yes.
But still having to do a bunch of like alignment of the red box. So for example,
yes,
you have this entropy condition, which you could imagine having to solve via a white box understanding of the red box. I think that's a simple picture to have, like intermediately.
Sorry, so you said if you have the entropy condition, but you don't have the specifications.
Like if you,
Is
if
that-
you need,
you're right.
you could imagine needed to get the entropy condition via alignment methods on the red box, but not having to solve specification.
So I'm not yet seeing, I'll have to read your paper. I'm not yet seeing how you could get the transfer entropy bound without having a lot of constraints on the solution that are making the measure of possible solutions small enough. But I do think that a complementary thing that perhaps should be worked on, but that would also reuse some of the work that we're doing here in terms of world modeling, would be if you have this part, you have this world model construction process, and then if you think that this is actually not very risky, then you could actually still just be iterating on potential solutions with respect to that world model, and have some panel of diversely aligned AIs that kind of look for problems and red team that solution for you instead of having a formal proof process for verifying that it satisfies some condition. Yeah.
That's a weaponry area where safeguard AI workflow could.
I am not going to do that. That's all I'll say.
I guess it's a high level question.
Yeah.
The economic incentives and also the competition between countries will mean that companies or governments will build super intelligent AIs in areas where you can't have formal specification.
Yes.
And a formal world. How do we avoid catastrophe here? I mean,
Yeah. So, okay. Yeah, so that I can speak to more directly. I have also been doing some work over the past year on hardware governance mechanisms, which could be used to verify agreements internationally about the use of compute, with the idea being that if you are using a lot of compute, then you must be using it in a way that is compliant with some agreements about how AIs should be safeguarded. And that could include evals and checkpoints and auditing and third-party red teaming and many other things. And it could also include, above some level of red flags regarding capabilities, that the only way in which the hardware will allow you to inference the system is inside of a workflow like this, in which the specifications are signed off on multilaterally. So that is a potential way in which this could actually be the standard international way.
We have a treaty that only allows this kind of thing.
Uh,
We have a way to verify that people actually do it this way.
That's the hope.
So there's another kind of bit of control the ASI has, which is like which problems it actually fails to provide.
That's correct.
Certificate for.
Yes.
Use that to steer the set of questions that are being studied in such a way that this transfer entropy bound is like pushed something.
Yes.
So how does one deal?
So one way of dealing with that is sort of analogous to the way that space launches are very expensive and risky, and so you will pack dozens and dozens of different experiments onto the same rocket. You could pack dozens and dozens of different problems into the same invocation. And just like a space launch, if it decides that it doesn't like one of them and it blows up, then you lose the whole lot. But you manage the risk. You could do it once a week and keep the transfer entropy to 50 bits a year.
It's like a high level of discipline.
It is, yeah. I mean, I expect we won't get as much of a bound on transfer entropy as we would need to avoid this kind of shaping of what kind of problems get solved. But I still think that if there are humans in the loop verifying the specifications and having collective deliberations about risk thresholds, this would avoid the worst possible outcomes from superintelligence.
I don't think I quite follow that. Like, if you pack them together and you have a non-constant bound, like, what is the reason why you wouldn't just get the sum of the bits?
Sorry, and this is addressing the specific point that you always get one bit. The AI always gets one bit for free, which is that it can fail every time you invoke it. And you can reduce that by packing problems into a single invocation and not accepting any of the solutions unless all of them check out.
Great, thank you.
Thank you.